Hey y'all, it's Mrs. Blasky. Today we're going to talk about topic 7.4, which covers acid-base properties of salt, or what is sometimes called hydrolysis. So everything that we've been talking about so far with acids and bases, we've been able to look at the formula of a compound and partially identify whether that substance is going to act as an acid, as a proton donor, or as a base, as a proton acceptor. Most of the acid-base substances or acidic substances that we're going to run into fit into those definitions. There are some cases, however, where something that does not obviously look like an acid or obviously look like a base can still have a pH other than 7. It can be something other than neutral. And so some of those substances look like good old-fashioned ionic compounds where we have a positive ion and a negative ion forming an ionic compound. So we have to look at these ionic compounds, which are sometimes called salts. That's an old-fashioned term for an ionic compound. And we need to break down that ionic compound or that salt into its two ions and analyze those ions to see, did these come from strong or weak acids and bases? So for example, we have some salts in the world that do not change the pH of water when it touches it. They're totally neutral. They do not change anything. One example here is sodium nitrate. So if I think about sodium nitrate, I need to think about which acid reacted with which base to form sodium nitrate. Where did that sodium come from? Where did that nitrate possibly come from to be able to form this substance? So if I think about it, I've got sodium and nitrate. Sodium is not going to come from an acid because it already has a positive charge. It wouldn't have that H plus on it to be able to give up. So sodium would have to have come from sodium hydroxide. We know that sodium hydroxide is a strong base. So 100% of those molecules of sodium hydroxide are going to dissociate and form sodium plus ions and hydroxide ions. The nitrate ion, NO3 minus, could be an acid. It could have had an H plus on it to neutralize that charge. That would be HNO3. That's nitric acid. That is on our list of strong acids. So these two ions, when they come from a salt or from an ionic compound, are not going to affect the pH. Anytime that sodium tries to come in contact with a hydroxide from the water, it's immediately going to dissociate again because that sodium hydroxide is a strong base. It does not exist together as a molecule in water. It will always exist as the separate ions. Same thing with the nitric acid. If a proton is around and tries to bond with that nitrate, not going to happen because that is a strong acid. Anytime a proton tries to be accepted, it's just going to break apart again. Remember that these strong acids and strong bases have weak conjugates. So their conjugates are not going to want to do anything. If I have an ion from a strong base and a strong acid coming together to form a salt, there is going to be no change in the pH. We call those neutral. If we have a salt that has one of its ions from either a weak acid or a weak base, then these are the ones that are going to be able to change the pH of our solution. So for example, if we think about potassium acetate, that's the wrong formula. It should just be K. Like there should be no 2 there. Potassium acetate is made up of K plus and our acetate ion. Again, if I think about this the same way as I thought about my sodium nitrate above, potassium would not be able to have a proton on it. It would have to come from the hydroxide. Potassium hydroxide is a strong base. So that is not going to be able to accept any of those hydroxides to be able to change the pH. But acetate, if acetate has a proton around, acetic acid, that's a weak acid. If that acetate ion is floating around in the solution and happens to accept a proton, it's going to keep that proton. Not all acetic acid molecules break apart because it is a weak acid. Only a small percentage of them will. So when that ion is in water, as this balanced equation is written out, it is going to be able to accept that proton and act like a base. So my acetate ion is acting like a base. My water is acting like an acid. And then I would have that conjugate of a strong base and that conjugate of a weak acid. I know also, if I see this balanced equation written out already, I know that this is acting as a base because I see that hydroxide ion in my balanced equation. If I see a hydroxide ion, I know that I could be talking about KBs. I know that my equation is going to be very specific because there's only one format for talking about equilibrium with acids and bases. On the other side, if I have a salt where the positive ion would form a weak acid or a weak base, then that is going to form an acid in solution. So ammonium ion, NH4 plus, is able to do this reaction. It is able to donate away a proton and act like an acid, which means that my water is acting like a base. Again, I would be able to write a Ka for this expression because I see that H3O plus in here. And we only ever have one format for Ka expressions. Or we could substitute in A minus and HA there. So when we're thinking this through, we need to look at the different ions that come from that salt, figure out which one of them is going to behave like an acid or like a base when in water. Is it able to accept or donate a proton just by itself as an ion? So let's try out a problem. We're going to have to do a little bit of flipping and a little bit of fancy footwork to be able to make these work. So let's take a look at number 46. That's a good place to start. So start off, first thing we need to do, read the problem. It says to calculate the pH of a 0.3 molar sodium fluoride solution, they give us a Ka for hydrofluoric acid. This is a hint. If they're giving me the Ka for hydrofluoric acid, but they're saying we have sodium fluoride in the solution, I know that hydrofluoric acid, HF, is going to have to show up somewhere in my balanced equation. So I'm not going to use the sodium. I'm going to use the fluorine ion. Again, if you're not sure what to look for, if we break up that ion, we're going to have sodium plus and F minus. If I have a hydroxide on that sodium, that is a strong base, sodium hydroxide, that is not going to influence my pH. But fluorine, if I add a proton onto fluorine, HF is a weak acid, which is going to influence my pH. It's going to accept some protons from the water and stay HF instead of immediately dissociating them again and not changing form too much. So when I write out my balanced equation for this, I'm just going to use the ion from the salt that is important. I'm just going to start with the F minus. So F minus is going to react with water Even if you don't think about, oh, I know it's an acid, or oh, I know it's a base, we should be able to look at this written out this way and go, is that F minus going to accept a proton or donate a proton? Well, it has no protons to donate, so it's going to have to accept one. So we're going to form HF. Water donated away that proton, so we're going to leave behind a hydroxide. Now, to be able to calculate the pH, I need the H plus concentration. I don't have an H plus concentration. I have an OH in my solution, but I know because of all those pH and KW equations that I can rearrange any of those numbers to be what I need them to be. So let's start off here. I know I have an ice chart. If I have an ice chart and I know my concentration of my NaF solution, if my sodium fluoride solution was 0.3 molar, it makes 1 fluoride ion for every 1 mole of sodium fluoride. Means that that's going to be the same concentration. Pure water doesn't show up in equilibrium. I start off with none of this and none of this. So I can solve this out. Minus X plus X plus X. And then now I have OH minus in my ice chart. That's a KB. I can only write a KB if I have a hydroxide in my equation. The problem gave me a Ka. I can't plug that straight into this equation to solve for anything, but just like H plus and OH minus concentrations are related to each other, Ka and Kb values are related to each other also. So Ka times Kb equals Kw. So I know that Kw is always 1 times 10 to the negative 14th. If I divide that by my Ka value, I can find my Kb. 1 times 10 to the negative 14th divided by 7.2 times 10 to the negative 4 is going to give me my Kb value. Gives me 1.39 times 10 to the negative 11. So now I can solve. 1.39 times 10 to the negative 11th equals X times X over 0.3 minus X. 5% rule says that that bottom X can go away. Excuse me. Algebra of that equation. X, which in this case is my hydroxide ion concentration, comes out to be 2.04 times 10 to the negative 6th molar. Now, they wanted me to calculate the pH. I have the OH. So if I take the negative log of this value, that's going to give me my POH. And then if I want to find my pH, I need to take 14 minus that value. To get my pH. So there's a lot of manipulation going on here. There's a lot of really identifying what am I talking about? Is this acting as an acid or base? And recognizing that pretty much every value that we're going to talk about is relatable to either an acid or a base if we are manipulating those numbers the right way. This is something we're going to keep working on. There are several practice problems in here. Make sure that you can identify if that ion is acting as an acid or as a base. I will see you all in class. Bye.